So this leads us into something which I think is really, really important to talk about, and it's called the Clouds Speech by Lord Kelvin. Now, Lord Kelvin, which is the name that the Kelvin temperature scale was given to, was a powerhouse in science, and he did a lot of work with thermodynamics and stuff like that, which was really cool. But Lord Kelvin got kind of arrogant, and in 1900 he gave a public speech, and you can look this up if you want, and he stated that current thermodynamic understanding basically has everything figured out. All right, there's a couple of these clouds which they hadn't figured out yet, but pretty soon even those were going to be worked out. And he essentially was discouraging people from going into physics and, in theory, all physical sciences like science. They truly, and it wasn't just Lord Kelvin, it was kind of the mentality at the time, they really thought that they had basically figured out everything in science. Okay. The clouds that they hadn't figured out, there were two main ones. There was something called the failure of the Michelson-Morley experiment. And that's not for this class to talk about, but it's really cool. And the important part here is that this failure, quote unquote, led to special relativity, which is one of Einstein's thing. And this is a really cool area to talk about, but it's definitely more of a physics thing than a chemistry. So just realize that this cloud that Lord Kelvin didn't understand led to something pretty cool. But even more important is that Lord Kelvin said, well, another cloud is the failure to understand black body radiation. And he says, but, we'll understand it pretty soon. Well, no, that didn't really happen. Black body radiation, the study of it, led to what's called quantum theory. Quantum theory is quantum mechanics, quantum chemistry, all this kind of stuff. So I look back on this, and you should too, at the arrogance of this scientist, Lord Kelvin. And he was a powerhouse. I mean, we still use the Kelvin temperatures all the time. We look back on this and you have to laugh a little bit, all right? He was definitely arrogant and was trying to figure it out. Let's talk about the ultraviolet catastrophe. The ultraviolet catastrophe is a really interesting thing. If you take a metal, all right, and you heat it up to really high temperatures, the color will change. Like first you get kind of a red color, then you get kind of a blue color, and you can even get white light. If you've ever heard the expression white hot, that's where it comes from, all right? So the energy of light does have a relative dependence on the type of temperature. And in the lower right-hand corner there, you can see the red light curve at the bottom, the kind of green light, 4,000 Kelvin, the blue white light, 5,000 Kelvin, et cetera, et cetera. According to classical physics, all right, they thought that you could just keep on maxing out the temperature, so you could go from 3,000 to 4,000 to 5,000 to 6,000, et cetera, and you'd keep on having more and more different kinds of things. But that's not what you saw. Classical physics just thought it would keep increasing. But really what happened is that at very high temperatures, there is a maximum intensity, and it's in the ultraviolet region, just a little bit to the left of the visible right there, but it does reach a maximum, and then it starts to go down. And this didn't make sense to classical physics. Like they thought, you just keep adding temperature, and it goes up. But that's not what they saw. They saw that it goes up for a little bit, but then it begins to decrease. Why don't you see like ultraviolet lines and stuff in just as much category? So this is called the ultraviolet catastrophe, and it has to do with how metals, and especially metals, behave under super hot conditions. And they thought that the temperature, the intensity would just go up, and in reality, it went up and then down.
A metal bar, like all objects at room temperature, emits infrared radiation. When heated to a relatively low temperature, however, the emitted radiation is in the red portion of the visible spectrum. As temperature increases, more light of shorter wavelengths is emitted until the bar glows white hot. In general, the hotter an object, the shorter the wavelength of light it emits. As the bar cools down, its glow returns to red.
So you can see in the animation there how as they heated it up, first it was kind of a red color, and then it got kind of a white color, like all different colors all together. And again, they thought that it would just keep going up and up and up, and you'd have lots and lots of ultraviolet and stuff, but you don't. There's like a maximum amount possible, and they called this the ultraviolet catastrophe. Along came a guy named Max Planck, and Max Planck proposed that an object can gain or lose energy by absorbing or emitting radiation in quanta, all right? And quanta was kind of an interesting idea, and no one had thought about this before. He proposed that the energy of the radiation is proportional to the frequency, all right? So he said that energy equals h nu. And this constant h was a brand new thing. And they figured out what h was. H is 6.626 times 10 to the minus 34 joule seconds. H is now called Planck's constant because Planck was the one that kind of brought this out. Planck is a powerhouse. One of the large universities in Germany is the Max Planck Institute, and they do some really high-level kind of stuff there. Planck was really cool in figuring out that, yes, you can understand the ultraviolet catastrophe if you have this E equals h nu. And there's a lot more detail to this than we're going to talk about here, but do realize. In the lower left corner, this is the Rayleigh-Jeans law, and it was basically the one by classical physics that just said it's going to increase until you never know. When you actually used Planck's constant and the ideas behind it, boy, the fit was perfect, all right? And there's a lot more to this, and we're just kind of glossing over it right now. But because the line and those dots are the same, that shows that Planck's function was a lot more effective at describing this ultraviolet catastrophe than the classical physics was. So knowing about Planck's constant is important, but they really had no idea how important Planck's constant is, and that's what we're going to see. Now again, the idea here is that the radiation that comes out of something, it's going to be quantized. There's going to be small little pieces associated with it, and each of those pieces has a frequency nu, and you can relate that back to the energy E by Planck's constant. So that's what we're going to focus on. We're not going to talk about the ultraviolet catastrophe as much as we are about how we can use this E equals h nu. E equals h nu, all right, and h is Planck's constant. V there is the nu, that's the frequency. And remembering that nu frequency equals speed of light over lambda, you can also write this as energy equals hc over lambda, where again, this is the wavelength, nu is the frequency, and they're both related to energy. Now, I'd like you to see that frequency nu and energy are directly proportional to each other. So as the frequency nu goes up, the energy is going to go up as well. On the other hand, the wavelength is in the denominator for energy. So as the wavelengths get bigger, the energy is actually going to decrease. And as the wavelengths get smaller, the energy will get larger as well. So notice here's kind of an overview. Light with large wavelengths will have small frequencies. They're inversely proportional. And large wavelengths will have small energies. Small frequencies will also have small energies. On the other hand, light with a short wavelength will have a large frequency. Again, they're inversely related to each other. And if you're going to have a small wavelength, you're going to have a large energy. We'll use these discussions here coming up, and you might look back on the types of frequencies which were dangerous in that last slide. You'll see that they're the larger frequencies. Larger frequencies mean larger energies. Got to be careful of those larger energy systems. Which of the following wavelengths represents the highest energy? Okay, so the first one is 47.1 meters, the second one is 47.1 nanometers, the third one 47.1 hertz. Now, let's talk about wavelengths again. Remember, wavelength is a distance, and hertz, Hz, that's actually a type of a frequency, all right? So C is not a wavelength at all. That's a frequency. That's bad. But so C is flat out, all right? C is a frequency, not a wavelength. On the other hand, A and B are both wavelengths. 47.1 meters is a lot bigger than 47.1 nanometers. So if you go back to the kind of gold thing right there, as wavelength gets smaller, then the frequency will get bigger, and as wavelength gets smaller, the energy will get bigger. So the biggest, highest energy is going to have the smallest wavelength. And in this case, the smallest wavelength is certainly the 47.1 nanometers. So in this case, small wavelength, large energy. 47.1 nanometers should have a bigger energy than the 47.1 meters. Good. After Planck, there was a lot of questions as to where Planck's constant came from, and nobody honestly had a very good idea at the time. But along the way, Albert Einstein, who probably you've heard of before, a really great scientist, started getting into the picture. Now, Einstein is really well known for a lot of different theories, and he's a really cool, interesting person to read about as a person. However, the thing that he got the Nobel Prize for, all right, is something called the photoelectric effect. And that's not as famous as like the general relativity and special relativity that he's well known for. But photoelectric effect is pretty cool. So I'd like to talk about photoelectric effect here because it does help us to understand what's happening in the atom. And photoelectric effect was something that was observed. Light emitted on a piece of metal can actually kick electrons off the metal. And I want you to just think about that, because light, if you beamed a flashlight at me, I'd be like, ha, but I mean, it wouldn't do any damage. I wouldn't like go flying backwards or something like that. Light seems pretty innocuous. But somehow when the light gets on the metal, electrons are emitted, and they have different ways and stuff. I'll show you a video here to kind of detect it. If you stop the light, then the electrons start kicking out. So it's definitely the light that's making this happen.
When yellow light shines on the metal surface, electrons are knocked out of the metal. As long as light of sufficient frequency shines on the metal, free electrons are produced and a current flows through the tube, as measured by an ammeter. The current stops flowing when the light is turned off.
The photoelectric effect is pretty interesting because it shows how light almost is acting like a particle. Like if you threw a particle at me, it would bounce off my head, but there would be interaction, mass and mass. It kind of makes sense. Momentum, if you're into physics, all right? But light doesn't have any mass, but somehow the light is able to make matter move, all right? The electrons, which are little pieces like a ball bearing or whatever, are able to move by that. So this is a really cool kind of thing. And apparently metal detectors and stuff like that use the photoelectric effect when they detect metals going through, things like that. Photoelectric effect helps to explain the particle nature of light. Now, I hope you're sitting down at this point because this gets a little weird. But light, all right, which is all around you right now, I would imagine, at least coming from the video, light actually has particle behavior. And that's weird. Now, a particle, like if you throw a particle at another particle, they bounce off, all right, momentum and stuff. But light doesn't do that, all right? But sometimes light behaves like a particle. And that's what the photoelectric effect is. Somehow it's like knocking into those electrons, dislodging them from the metal, so they go flying out the opposite side. Classical physics said that the energy of the ejected electron should increase as the light intensity increases, and that kind of makes sense. So if the electrons are getting kicked off, you then have more intense light. You'd think you'd have higher energy electrons, but you don't see that. There's like a threshold value that you need to attain, and then it's basically a constant. So there's no electrons observed until you get to a light of a certain minimum energy. And as we saw, energy is proportional to frequency, so it could be a minimum frequency. And again, this was pretty wild kind of stuff. It still feels wild to talk about it even today. Light is said to display a wave-particle duality. Let's talk about what that means. Wave-particle duality means that light, which is electromagnetic radiation, wavelength, frequency, all that kind of stuff, behaves often like waves, but sometimes like particles, all right? So light will behave like a wave in diffraction, interference, if you know about these kind of things, but it can also behave like a particle in the photoelectric effect. And this was like, whoa, man, this totally blew scientists' mind, because light is light, right? You know, you aim a flashlight and stuff like that, or heat, or blah, blah, blah. But it doesn't behave like a particle. And we're going to see it's not just light that has wave-particle duality. There are other things that have wave-particle duality. And again, that just means that sometimes it acts like a wave, sometimes it acts like a particle. And that's so trippy. But Einstein was the first one to crack that egg open. And oh my gosh, here we go. Experimental observations can be understood if you break light down into discrete particles. Quanta is what Planck called them. Let's call them photons. And the photons have discrete energy. So quanta is basically an early name for what we're going to start calling a photon. So let's say that we wanted to calculate the energy of 1 mole of photons of red light. And let's say that the red light has a wavelength of 700 nanometers, all right? And earlier, when we did 700 nanometers, we found that the frequency was 4.28 times 10 to the 14th inverse seconds, or hertz. We're going to use that number here in a little bit then to calculate the energy. So this is kind of cool. Energy equals h times nu, according to Planck's constant, or hc divided by lambda. Just remember that you want to make sure your wavelength is in meters. Right now, of course, it's in nanometers. So let's use the frequency just because the units are set up. Now, Planck's constant, 6.626 times 10 to the minus 34 joules seconds, joules times seconds, which is weird, but those are the units and it makes things work out. It is joule times seconds because frequency is 1 over seconds, or seconds minus 1. So the second on the top cancels the second on the bottom. You end up with so many joules. So 1 photon of this red light at 700 nanometers has an energy 2.84 times 10 to the minus 19th joules per photon. That's a super small amount of light. All right, we were looking in the last chapter, Hess's law, or delta H products minus delta H reactants. Reactions were in the kilojoules. So this is a pretty small number, okay? This is the energy per photon of light. But we want to know the energy for 1 mole of photons. So let's take that number, the joules per photon, and turn it into joules per mole. And just like we did when we turned atoms into moles, we used Avogadro's number. Here we're going to use Avogadro's number, but as 6.022 times 10 to the 23rd photons per mole. Again, Avogadro's number is just like a dozen. You can use it in anything you want. We've used it in atoms per mole, molecules per mole. Now we're using it in photons per mole. Oh my goodness. But anyway, joules per photon times photons per mole, the photons pH will cancel. You initially have joules per mole, that 171,000 number. A lot of times people will convert it into kilojoules, 1,000 joules per kilojoules, 171 kilojoules per mole. And this energy is actually the same magnitude as a lot of the delta H products minus delta H reactants problems we did in problem set number 5. And what that means is that red light at 700 nanometers is capable of breaking bonds. You can enact chemical change by doing nothing more than putting red light on it. And this is a cool kind of chemistry called photochemistry. You set your reactants up, you basically turn the light on, you go away for the weekend and study in the library all weekend. Not. Anyway, you come back on Monday, whatever, and you've got your chemicals made. If you can calibrate the energy of your light to the energy of the reaction, products minus reactants kind of thing, you can do this. Photochemistry, I think, would be such a cool field to be into.